Hi, in this video, we will discuss how to find the sound spectrum using the octave band. In this example, we have a shaker move horizontally back and forward in order to produce alternating compression as well as the rarefaction at a single frequency. So you can see in the time domain, we have a sinusoidal wave, and if we convert it to the frequency domain, we obtain a single frequency component of the sound spectrum. So the conversion from the time to frequency can be done by using the fast Fourier transform. In the second example, the vibrating piston moves cyclically in a reciprocating manner. So you can see there is multiple frequency 1 and multiple frequency 2. So in this case, the alternating compression and the rarefaction is produced at multiple frequency. So if we plot the time domain signal, we obtain more complicated signal, and if we convert it to the frequency domain, we see several cyclic frequency at the sound spectrum. So we know that noise can be defined as undesired sound or unwanted sound, which normally has very high sound pressure, and is usually composed of many frequencies combined together. So for example, in this case, we have a very complicated time domain sound signal where after we perform the fast Fourier transform and after we perform the octave band filter, you obtain some result like this, where you see instead of a single or multiple frequency data, we see a lot of frequency band, where the frequency data is arranged in a bunch of frequency range. So for example, in this case, the frequency range is from here to here, and we use the bandpass filter in order to obtain this value. We will discuss more about the octave band filter in the measurement chapter. At the moment, bear in your mind, for the sound spectrum, we have some frequency band like this, and this frequency band is obtained by using the octave band filter. We have more noise example for the noise data in time and frequency domain. For example, in this case, we have the gear system, where you can see the data is harmonic, and when we convert to frequency, we obtain the sound pressure level in this manner, where the sound is normally high at the 1 times running frequency, 2 times, 3 times, 4 times, and so on. So this is the running frequency for the gear system. When we take the sound measurement for running, so in this case, we obtain more random data in the time domain. And the noise after you convert to the frequency, so we obtain the sound pressure level in a broadband manner, where you see the magnitude of the pressure is almost constant for a broad range of the frequency. For impact activity, we will obtain impulsive sound behavior like this, where the sound increase significantly at the beginning and reduce and decay to 0 over time. In frequency domain, the characteristic of the impulsive sound has a broadband characteristic, where you can see that the magnitude of the sound pressure decrease over the frequency. So we see the type of noise is characterized by its frequency spectrum and its variation as a function of time. Based on this ISO, we can classify the noise into steady, non-steady, impulsive, depending on the temporal variation in sound pressure level. First of all, steady noise is a noise with negligible small fluctuation of sound pressure level within the period of observation. So for example, let's measure the sound from this activity and you obtain signal like this. And we can see that it's a constant continuous sound with negligible small fluctuation. From the time domain signal, you can see that the sound is within 5 dB. So in this case, we can call it to be a steady or constant noise. Non-steady noise is a noise with the sound pressure levels shift significantly during the measurement. It can be divided into fluctuating noise and also the intermittent noise. If you take the measurement at this activity, so most probably you will obtain the sound measurement to be this signal. In this case, we can see that the noise is fluctuating and the level changes significantly over 10 dB. The signal is complicated and it is a non-periodic sound. For this type of noise, it consists of a lot of frequency components. In this case, we have a large fluctuation where the level changes over 10 dB. If we examine the noise, we found that it is a periodic sound. Therefore, for this type of sound, it consists of one or two single frequencies only, and we can call it to be tonal noise. In practical, tonal noise is more annoying than the broadband noise, so we should avoid this. Intermittent noise is another type of non-steady noise for which the levels drop to the level of background noise several times during the period of observation. For example, here you can see that the noise dropped to the background noise here and increase intermittently. So this type of noise can be found in this activity. You can see the characteristic of the sound is constant like this, but it changes intermittently with the background noise. For the impulsive noise, it consists of one or more bursts of sound energy, each of the duration less than 1 second. For the type A impulsive noise that is generated by the explosive event, such as the gunshot, so you should obtain signal like this, where this is the impulsive duration. For impulsive event, you have a very high amplitude of the noise, where the AB here is the peak level. The rise time from A to B happen in a very short time manner. These are some important parameters when we study the type A impulsive noise. For the type B impulsive noise, it is generated due to the impact event, such as the punch press impulse. For example, imagine you have a punch hammer here and you record the sound for this punching activity. When the punch moves and hit to the surface here, the sound increased significantly at the beginning. Due to the impact hammer is connecting to the surface while the surface is oscillating due to the impact. Therefore, you see there is an oscillating, decaying response afterwards. If the removal of the punch hammer is not fast enough, then refraction towards the punch hammer will happen, and this will cause the refraction. And in this case, you obtain second impulsive due to the refraction. The peak level can be obtained from the pressure difference between A and B. Rise time can be obtained from the time difference between A and B, and the B duration can be obtained between A and D, where you can see the sound pressure level is decreasing by 20 dB. So at the beginning A here, okay, after the sound decay to 20 dB, at this point is your D. So when you take the time between A and D, it will be the B duration. However, in some cases where the refraction happens, you have the second impulsive sound here. So in this case, B duration is obtained by taking the summation of the time AD plus the time EF here. For other engineering activity like this, you may obtain repeated impulsive signal where there is a lot of similar impulsive happen in a short range of time, or you might have a single impulsive where you see isolated impulse happen over time. These are under the type B impulsive noise as well. For vibration engineering application, if you have a time domain vibration, after you convert it to the frequency domain, if the vibration here is oscillating, then you should obtain the frequency domain to be various peak data, where each of them represent a single frequency. For the vibration analysis, we prefer to have a very small delta f, which represents a very high resolution for our frequency domain. However, for the sound analysis, the frequency domain analysis here, the approach is different. Instead of discrete frequency data, in sound spectrum, we have frequency band, where in the frequency, we group the sound data into several frequency range, which is called the band. The common sound spectrum is known as 1-to-1 octave band. In general, you might see the symbol for 1/1 or 1:1. Both of them represent the same thing. This is the 1-to-1 octave bands given by the international standard. So you don't need to memorize this. Always use this as the appendix. Since human can listen sound from 20 Hz up to 20 kHz, 1-to-1 octave band divide the audible sounds into 10 bands. So this is the first band, and we can continue for the second band, third band, and so on until the last band. So in total you have 10 bands that covers the frequency around 20 to 20 kHz. For the first band, you can refer to this chart to find the lower band limit, center frequency, and also the upper band limit. So you have 22 Hz, which is this 22, and 44 is the upper frequency. For the center frequency, it will be 31.5, which is here. The second band is located from 44 to 88 Hz, which is 44 to 88 Hz here. So this is your second band, and the center frequency is given by 63. So you can continue up to the last band, which is the band number 10. So the lower frequency is 11K, and the upper frequency is around 23K. The center frequency is 16K. So this is the last band. This is the example for the 1 octave band that you obtain follow the international standard here. For clarity purpose, normally we only have the center frequency labeled in the sound spectrum. For example, the center frequency is equal to 31 Hz at the first band. For the second band, it will be 63. Third band is 125, and so on. To find the lower band limit, we can divide the center frequency by square root of 2. So take the 31.5 divided by square root 2 should give you 22. And to obtain the upper band limit, you take the 31.5, which is the center frequency, and multiply it with the square root 2. By doing this, you obtain the upper band limit. Let's find the lower band limit and upper band limit for band number 7. By referring to this standard, the center frequency is 2000, and from here, if you divide it with square root 2, then you should obtain this number. To find the upper band limit, just take the center frequency and multiply it with the square root 2. Then you should obtain this answer. From the 1 octave band sound spectrum here, you see the band 7 possesses the highest sound pressure level. So in this case, we can say that the noise happened at this frequency range, which is from 1.4 kHz up to 2.8 kHz. We see that the range here is very high, and the frequency resolution is not that Good. In order to improve the frequency resolution, we can further split the band here into 3 bands. So imagine that each band separate into 3 bands. Initially you have 10 bands, so in total you can split it into 30 bands. Then you can obtain the 1 to 3 octave band, where we divide the audible sound into 30 bands. So the audible sound is from 20 to 20 kHz. So if you plot the graph from 20 to 20 kHz here, now instead of having 10 band, we are having 1, 2, 3 up to 30 band. So this is the first band frequency. So your first band has the center frequency equal to 25, lower band limit equal to 22, upper band limit equal to 28. So this is the first band. You can continue for the 30 band, okay, which is this. So the lower limit is 17K, upper limit is 22K, and the center limit here is 20K. Right? So the purpose of having 1-3 octave band or the 1-1 octave band is depending on whether you want a better frequency resolution or not. If you prefer a better frequency resolution, then we will go for the 1-3 octave band. So far we have learned that the hearing range for human is from 20 Hz to 20 kHz. If we separate the hearing range into 10 bands, then by using the 1-1 octave band standard, we can obtain the corresponding lower frequency limit and upper frequency limit for each of the band here. Since we know the speed of the sound propagate in the air around 20 degrees Celsius is equal to 343 meter per second. By using this formula, where we treat the C to be constant as long as the medium doesn't change, so in this case, by substitute the frequency, we can obtain the corresponding wavelength. For a piano, it consists of 7 octave bands, where this is the first band, this is the second band, third band, fourth band, fifth band, sixth band, and seventh band. Let's play the piano for the first octave band here. So this is the C1 note, which is representing the Do note. You are listening to 7 sound playing at this 7 note here. Let's continue to play the piano at the next octave. You should be able to listen and recognize that the sound has the same rhythm as the previous piano note. However, the frequency is slightly increased. Let's continue to play the piano notes for the next 3 octave band here. It consists of 21 notes. So you can see that for each octave band, the rhythm are the same, but the frequency increased from one to another, higher and higher. This example should give you some idea about what is the octave band. This can be demonstrated by using a piano. So piano can produce sound from around 31.5 to 4 kHz. And you can see that when we are younger, the frequency range is broader. But when we are old, the frequency range, especially at the higher frequency region, is diminished, where we cannot listen to this region anymore. And the frequency range is reduced to a shorter range, same like the sound produced by the piano. For normal speech, the sound produced is normally between 125 Hz up to 8 kHz. For the acoustic lab test, we normally focus on this frequency range.